Give yourself just two tools, a compass for drawing circles and a straight edge for drawing lines, with no marks on it for measuring. With only those two, how many sides can a perfect regular polygon have? A regular triangle is easy, so is a square. The regular pentagon takes a little cleverness, but the Greeks had it more than 2,000 years ago, and the six-sided hexagon almost falls out of the compass on its own. So far the answer looks like it could be anything. Pick a number of sides, and surely with enough patience you could draw that shape. Now try to draw a regular seven-sided figure. A perfect heptagon, 7 equal edges and 7 equal corners. You can sketch something close by eye, but a true one, exact, with nothing but the compass and the straight edge, nobody can. Not because we have not found the trick yet, because it is impossible, and that impossibility was proven. The same goes for 9 sides, and here is the part that turns a drawing puzzle into something deeper. Which polygons you can build, and which you can never build, is decided by a short list of very rare prime numbers, and only 5 of them are known to exist. By the end of this, you will know exactly which shapes are allowed, and why the whole question comes down to those 5 numbers. To see where the wall is, we first have to be honest about what those two tools can actually do. Put the whole drawing on a grid, so every point is a pair of numbers. A straight edge through 2 known points draws a line. A compass draws a circle around a known point. New points appear where a line crosses a line crosses a circle, or a circle crosses a circle. If you write down the arithmetic for those crossings, every new coordinate comes from the old ones using only 4 operations and 1 more. You can add, subtract, multiply, divide, and you can take a square root. That square root is the one interesting power the compass gives you, because finding where a line meets a circle means solving for a length that squares to something, and nothing harder than that ever shows up. So the reachable lengths are exactly the numbers you can write starting from 1 using those operations, with square roots stacked as deep as you like. A square root of a square root is fine. A square root of a sum of square roots is fine. What you can draw with compass and straight edge is precisely what you can write with whole numbers and nested square roots, and not one thing more. Keep that sentence in mind, because every yes and every no in this whole story is just that rule being applied. To build a regular polygon with a certain number of sides, the corner positions have to be numbers of that kind, and when they are not, the shape is simply out of reach. So let us walk into the wall on purpose and watch it stop us. Take the regular 7-sided polygon, drop its corners evenly around a circle, and the horizontal position of the first corner away from the center is a specific number, the cosine of 1/7 of a full turn. That single number decides everything, because once you can mark it off, the rest of the corners follow by stepping around. So the only question is whether that one length is reachable, and when you grind through the algebra, that cosine turns out to satisfy an equation that genuinely needs a cube root to solve. Not a square root, a cube root. And a cube root is exactly the thing our two tools cannot reach. We just said the compass only ever hands us square roots of square roots, sums of those, but never a clean cube root out of nowhere. A length that truly requires 1 is forever outside the set of things a line and a circle can produce. So the regular 7-gon is not hard, it is barred. The same wall stops 9 sides, for the same reason. The corner you would need lives 1 floor up in a world of cube roots that the compass has no key to. Seeing one shape fail this cleanly tells you the rule has teeth. The next surprise is which shapes sneak past it. For about 2,000 years, the regular polygons people knew how to draw were basically the obvious family. 3, 4, 5, 6 sides, and the shapes you get by repeatedly cutting an angle in half. Cutting an angle in half is one clean compass move, and halving only ever asks for a square root, so it is always allowed. That is why a hexagon gives you a 12-gon, then a 24-gon, doubling forever. From the triangle you reach 6, 12, 24. From the square, 8, 16, 32. Useful, but it felt like the whole story, and for 20 centuries nobody added a genuinely new odd shape to the pentagon. Then in 1796, a 19-year-old named Carl Friedrich Gauss found something nobody expected. The regular 17-sided polygon, the heptadecigon, can be built with compass and straightedge. 17, a prime number, sitting in the gap between the buildable shapes and the barred ones, and it lands on the buildable side. Gauss showed that the key length, the cosine of 1/17 of a turn, is not some hopeless cube root creature at all. It is a tower of nested square roots, written out of ordinary whole numbers, and so it falls squarely inside what the compass can reach. He was so taken with it that he asked for a 17 gon to be carved on his gravestone. The story goes that the stonemason refused, on the grounds that it would be indistinguishable from a circle, but the proof was the thing that mattered, and it cracked the question wide open. If 17 works and 7 does not, then the rule for which polygons are allowed is hiding inside the prime numbers themselves, and Gauss had just found the first clue to it. The clue lives in a family of numbers invented long before, by Pierre de Fermat, and they are built by a strange little recipe. Start with 2, raise it to a power that is itself a power of 2, then add 1. The first few come out small and friendly. 2 to the first plus 1 is 3. 2 squared plus 1 is 5. 2 to the fourth plus 1 is 17. 2 to the 8th plus 1 is 257. And 2 to the 16th plus 1 is 65,537. 5 numbers, 3, 5, 17, 257, and 65,537. Now check each of those 5 for primality, and every single one is prime, divisible by nothing but itself and 1. Fermat noticed this run and made a bold guess, that the recipe spits out a prime every single time, forever. And you can feel the temptation. 5 clean primes in a row, growing fast, each one passing the test. It is exactly the kind of pattern that looks like a law of nature. These 5 are now called the Fermat primes, and the reason they matter to our polygons is about to become the whole point. Hold on to the fact that there are exactly 5 of them that anyone has ever found. So take the recipe one step further, the way you always should when a pattern looks too good. The next number is 2 raised to the 32nd power, plus 1. That comes out to 4,294,967,297. A 10-digit monster, and far too big to check by hand in Fermat's day, which is exactly why his guess stood unchallenged for almost a century. Then in 1732, Leonhard Euler sat down with it and found that it is not prime at all. It breaks cleanly into 641 times 6,700,417. 2 ordinary factors, and the supposed law of nature was dead on its 6th step. And it gets lonelier from there. Every Fermat number that anyone has managed to test past the 5th one has turned out to be composite. We have checked them up through the 32nd, and a great many beyond, and not a single new prime has appeared in the entire family. So as far as anyone knows, the Fermat primes are just those 5 small ones at the very start, and then nothing, possibly forever. Whether a 6th one is hiding somewhere out in the unimaginably large numbers is a question nobody has answered. Keep that uncertainty in your back pocket, because it is the reason this story has an open ending. Now we can finally state the rule that ties the polygons to the primes, the rule Gauss saw the shape of. A regular polygon with a given number of sides can be built with compass and straightedge exactly when that number of sides is a power of 2 multiplied by a set of different Fermat primes, with no Fermat prime used twice. That is the whole law. The powers of 2 come from halving angles, which we get for free. The Fermat primes are the only odd ingredients allowed, and you may pick each one at most once. Anything you can assemble that way is buildable. Anything you cannot is barred. Watch it decide the small cases instantly. 3 is a Fermat prime, allowed. 4 is 2 times 2, allowed. 5 is a Fermat prime, allowed. 6 is 2 times 3, allowed. 7 is a prime, but it is not a Fermat prime, so it is forbidden. Exactly the wall we hit earlier. 8 is 2 cubed, allowed. 9 is 3 times 3, and 3 is only allowed once, so 9 is forbidden too, just as we found. 10 is 2 times 5, allowed. The full list of buildable polygons up to 100 sides reads 3, 4, 5, 6, 8, 10, 12, 15, 16, 17, 20, 24, 30, 32, 34, and on in that pattern. Every yes on that list, and every gap where a no belongs, is just this one rule sorting the numbers. Gauss proved the easy direction, that every number of that special form really can be drawn. But he left the harder half hanging. It took until 1837, when Pierre Wantzel proved the other direction, that no other number of sides works, ever. If your shape is not a power of 2 times distinct Fermat primes, it is genuinely, provably impossible, no matter how clever you are. That is the half that turns the rule from a recipe into a wall. Together, the two halves say the buildable polygons are precisely these and no others, with nothing left to discover by trying harder. And now the strangeness of the title comes home. The odd building blocks for every constructible polygon are the Fermat primes, and only 5 of them are known to exist. 5 numbers: 3, 5, 17, 257, and 65,537 are the entire odd vocabulary for this whole infinite question. The 257-sided polygon is buildable, and someone worked out how. The 65,537-sided one is buildable too. And a mathematician named Johann Hermes spent about 10 years of his life writing down the full construction, a manuscript that still sits in a box at a university. Those giant shapes are allowed only because their side counts are Fermat primes. And since no 6th Fermat prime has ever been found, this little set of 5 may be all the odd ingredients that will ever exist. So here is the whole shape of it, start to finish. A compass and a straight edge can only reach lengths made from whole numbers and nested square roots. A regular polygon is buildable exactly when its corner positions are lengths of that kind, and that happens precisely when the number of sides is a power of 2 times a few distinct Fermat primes. The 7-gon and the 9-gon fail because they would need cube roots the tools cannot make. The 17-gon succeeds because its key length is a tower of square roots, which is what Gauss found at 19. And the open door is still standing wide. Everything here rests on those 5 Fermat primes, and nobody knows whether there is a 6th. Every Fermat number tested past the 5th has been composite, all the way out as far as anyone has pushed, but no one has proven that the supply truly stops at 5. If a new Fermat prime were ever found, a brand new buildable polygon with a colossal prime number of sides would snap into existence along with it. The oldest tools in mathematics, a circle and a line, turn out to be governed by one of its most stubborn open questions. If there is one thing to carry away, it is that whether you can draw a shape with a circle and a line is secretly a question about prime numbers, and the answer hangs on a list that might only ever have 5 entries on it. This was one more in a series on how a single person settled one hard question. Stay for the rest.